I'll start with the talks this afternoon. So there are 3 talks, all are 30 minutes long, and I'll stop 25 minutes after the talk starts, and then there's some time for questions. The first speaker is Yoram Lithwick. He's an assistant professor at Northwestern, and he's going to tell us what he can learn from Kepler.
Hi. So I'm going to talk about some of the stuff we learned from Kepler. First thing is chaos. Okay, so we've seen this plot a few times already. A number of people have shown this. This shows how great the Kepler telescope is, how many discoveries it's had. It's discovered thousands and thousands of planets. They're very different than what we find in our solar system. So this Mercury, our closest planet, is 88 days. So most of them are inside 88 days. And most of them are smaller than Neptune and larger than Earth. So it's an unusual type of planet. I'll just call them Kepler planets for short. And these are actually ubiquitous. They're around 20–30% of all stars have such planets, which is unexpected. Perhaps even more remarkable is not just the sheer number of planets, but the fact that lots of them are in systems. So this is a famous Kepler 11. There are 6 planets, and all of them transit the star. In order to see what Kepler has to transit the star. And this shows the multiplicity. In other words, there are around 300 systems that have 2 planets, almost 200 that have 3, this one have 4, all transiting planets. So this falls off very gradually. So it's very surprising. There's so many systems with high multiplicity, 5, 6, 7. Especially when you take into account the fact that it has to be oriented right for all the planets to transit.
Why is it surprising?
Well, okay, it's I could go into.
Since we had no idea what.
Since we had no idea.
Kepler, why are you surprised?
Well, I guess rather than surprising, I'd say it's remarkable. It's a remarkable thing that was completely unexpected, so it could go on either way. And it's very different than the intrinsic set of planets. When you do population studies, you find that around 1 out of 3 of these systems are intrinsically very flat, and they host many planets, 6 to 8 planets in a decade of semi-major axis, which is more closely packed in our solar system than the terrestrial planets in the solar system. Also, from the fact that this follows gradually, with the multiplicity, you can infer something about how inclined the planets are. Because if they're very inclined, it's unlikely to transit, for many of them to transit simultaneously. And you can get an upper limit on the inclination, the spread in inclination is about 5 degrees. Another reason that these guys are actually surprising is that there was a prediction before Kepler telescope launched for where you'd expect to find the planets. And so they predicted that this is the vicinity of where the Kepler planets are. So the black dots are their prediction, and they predict basically there'd be no planets in that region. Whereas you see that there are lots and lots of planets in that region. This is a real surprise. The basic reason why Bell got it wrong is still there's a fundamental problem which we still face, which is type 1 migration. In other words, if these planets are put in their position by a gas disk, if they're put in their place by the gas disk, the problem is the gas disk causes these planets to zoom really fast. So it's the type 1 migration problem. So planets in the disk just fall into the star on a 1,000-year time scale, which is much shorter than the age of time scale of planet formation, which is about 1 million years. So if you try to put planets in this region, they all zip into the star. So you have to do something else to prevent them from falling into the star. So something's wrong with type 1 migration, or something has to be modified. So what else can we learn about Kepler planets? So it's a really exciting population that we could hope to study to learn about planet formation. The basic data that Kepler tells us for all these thousands of planets are their sizes, And the reason, so Kepler is a transiting telescope, so it sees the dip in the light when the planet transits up to the star. So based on the amount of dip, that tells you how big the planet is relative to the star. That's one bit of information. The second bit of information that Kepler tells you is the period, how long it takes for the planet to do a second transit. So for those thousands of planets, we basically know their size, relative to their star size, and their periods. But we'd also like to know other information about the planets, like we'd like to know their masses, and we'd like to know their eccentricities. So how can we do that? So one of the most promising ways is with transit time variations. The basic idea is that if you have a single planet, there's only one planet which is orbiting the star, and you can look at the times of transit. So you plot, these are the black ones, plot the times of transit as a function of transit number, and it just rises linearly because the Keplerian orbit is periodic. You can put in two planets and they tug on each other back and forth, and that leads to these wiggles in the times of transit. And I've greatly exaggerated the amount of wiggle here, just so you can see it. So these wiggles, if you just subtract off the flat line, that okay, so you just get it's typically a sinusoidal type pattern. These are the transit time variations, just these wiggles. And this is actual data for actual planets, Kepler 18. And these wiggles can be used to tell you about properties of the interacting planets. This is the inner planet of the Kepler 18 system and the outer planet. And they both have transit time variations, and you can use them to infer about the masses and eccentricities. So to try to use this transit time data to learn about the masses and eccentricities, so what we did is we derived a simple formula for how the planets interact with each other and how that gives rise to transit time variation, or TTV. And the formula in drop-in constants is basically this. So this shows the transit time, the TTV curve after subtracting out the constant line. And there's an amplitude to the TTV curve. And the amplitude is basically given by this. So there are three factors in here. One is the mass and eccentricity. And those are the things we'd like to measure from the TTV. The other thing is this delta. So this delta is how close, this pair of planets is how close they are to resonance. This number is known for any pair of planets. You can actually see it because you know the periods of the planet. It's typically a few percent for the pairs of planets that have observed TTV. You'd like it to be small to boost the signal. So we know this number, and we'd like to know the masses and the eccentricity. So there's good news and bad news with this formula. The good news is it's exquisitely sensitive to the eccentricity, because you see you have the factor of E over delta. Delta is typically a few percent. So you can actually use TTVs to measure the eccentricities to a precision of a few percent. The bad news is that there's a mass and eccentricity degeneracy. You can boost the eccentricity and decrease the mass without changing the amplitude. But there's one more bit of information that we can use, and that's a phase of the whole TTV signal. So the TTV signal there's a well-defined phase of where the TTV signal is, and that gives extra information. And so to encode this, instead of using an amplitude to give the TTV signal here, you can use a complex number, which has both an amplitude and a phase. And this V is now a complex number. And the only way the complex number comes in is that it multiplies this E by E to the I omega, which is going to put this one. So this complex number, this is actually the eccentricity vector in a complex form. Whenever you have eccentricities, they always enters via the eccentricity vector. So it's natural to have a complex number here. And that's what gives the phase shift. This is the only way to make this number complex is to make this complex. And so if the eccentricities are very small, this term goes away, and your V is real. So that means it has a well-defined, the TTV pattern has a well-defined phase. If the eccentricity is very big, then this term dominates, and you can have all kinds of random phases. So what you can do is you can look at for any pair of planets, look at their TTVs, and there are hundreds of planets now that have TTVs measured. Look at their phases, and based on the phases, you can infer what the underlying eccentricities are. So this first shows a simple model where I imagine that I take a set of imagined planets. I imagine that they all have eccentricity RMS eccentricity about a third of delta, where delta is typically a few percent, but for this exercise it doesn't matter what it is. So if the eccentricity is a little less than delta, and you look at the distribution of phases, you see it's really sharply peaked around 0. So they're all the TTV curves have exactly the same phase. If the RMS eccentricity is a little bit bigger than delta, then you get a very broad distribution of phases. So what we want to do is we want to invert the observed distribution of phases. This is just a model. So that's what we did. This shows these red histogram is the actual observed phases. This black line is the fifth of the observed phases. This is an inner planet and this is the outer planet. These are two planets that interact with each other. And you can infer from this, you can fit these and infer an eccentricity, an RMS eccentricity for the distribution, assuming they all come from an similar underlying distribution. And what you find is that the RMS eccentricity is this. So it's around 2% with pretty small error bars. So there are a few remarks to make about this. So first of all, these eccentricities are much lower than what's found for the higher mass planets, the Jupiter mass planets, which typically have eccentricities of around 0.1 or 0.2. So these Kepler planets, smaller than Neptune, almost certainly form very differently than those planets. Another thing to note is this number is close to 0. These are solar system-ish values for terrestrial planets. It's close to 0, but it's distinctly different than 0. And you can even look at the actual phases. These are the individual phases for individual planets, and many of them are inconsistent with being 0. So it's clear that these planets do not have 0 eccentricity, which is again somewhat surprising. It might be surprising if all the planets experience damping. You might expect that all the eccentricities would relax to 0, but instead they have some finite eccentricity. And so this measurement just emphasizes that this is pretty robust. There's basically no way out of this argument. It just depends on the phase of the TTV. You don't care about the stellar parameters or uncertainties like that. So another thing we can learn from the TTV is the masses of the planets. And I won't talk about this too much. My focus is going to be on the eccentricities. But I'll just say that given the masses, we already know the radii of the planets. So with the masses and the radii, we know the densities of these planets. And I guess the most remarkable thing is that if you plot the radius of the planet versus the density, there's a very steep fall off. As you increase in radius, as you look at planets which are slightly bigger than Earth, like Neptune and Uranus size, they're all very, very underdense, much less dense than water. So planets that are just a little bit bigger than Earth have to be covered completely in hydrogen gas. There's basically no way to make such a big planet without having a significant amount of hydrogen gas. There's at least 10% or more by mass of hydrogen gas. If the planet is slightly smaller, there's a steep rise. It suddenly gets, planets get denser and denser. And then this trend is also found, so you can also infer masses from radial velocities. So I'm not showing the data now. But it basically agrees with this pretty well. People follow up these planets with radial velocity measurements. It's much more expensive than using TPV.
Excuse me, I thought there was some disagreement between TPV and radial velocity.
Yes, there's claim disagreement with the claims.
There was a systematic.
There's claims that, and well, I know exactly who you're referring to.
Well, there are several people who.
Right, so when they make that claim, they're only referring to about 6 or 7 planets which have. Well, I can show you the slide after. It's only 6 or 7 planets in 2 systems. So those are the ones which had published TTV when they made the claim, and they didn't compare with our data, which has many more. So if you just plot their data on top of ours, it agrees quite well. This hour, the Kepler 11 is one of the systems, and there's a second system. Okay, so let me jump to the second thing that we can learn about the Kepler planets. And this is resonant repulsion. So since there's so many systems of planets, we can look at the spacing between the planets. This shows the histograms. If you look at all pairs of Kepler planets, and you look at their period ratios, you can plot up a histogram. This is what the histogram looks like. So I guess the first thing to notice is that most of the planets are quite close together. They're sort of around 2 to 1, 3 to 2. This is sort of where the Earth-Venus separation is. But it's not just Earth and Venus are pretty close to each other, but there are multiple planets which are all as close to each other as Earth. But okay, so at the 0th order, there's basically all you see is roughly a palop around 2 to 1. But and there's not much of a feature near resonances, so near 2 to 1 and then 3 to 2. But if you look with a magnifying glass, or if you look very closely, you can see there's a dip inside of the 2 to 1 and a rise outside of the 2 to 1. And similar for other resonances, 3 to 2, which shows a modest dip but a very large rise. And then 4 to 3, so they often show the symmetric pattern, palop outside and depths. So there's a few mechanisms which have been proposed to explain this, and viewed by multiple people in this room. I'll just focus on the one that I've worked on, which is the first, resonant repulsion. So the basic idea of how you get this palop outside of resonances is that you just add damping to the system. So if I start out planets that just randomly distributed in their period ratio, and I just add damping, then I naturally get a deficit inside and a palop outside. And so I'll explain briefly how it works. So let's think of a planet. This blue guy is a planet. He's orbiting the star. And we'll think of a test particle. So instead of 2 planets, it's easier often to think of a massive body in the first place. This test particle is going to be near the 2 to 1 resonance of this planet. This planet's going to be going on a circular orbit. And I'm about to show a movie, and the movie's going to be in the reference frame of the blue planet. So what happens at first is the red guy goes all over the place. It's perturbed because it's near the 2 to 1, so it gets a big pick in eccentricity. And I've exaggerated the amount of eccentricity. But then I've also added a little bit of damping to the simulation. And the form of the damping is not important. Almost virtually any damping has a similar effect. And the effect that you see is that it goes to a characteristic shape. Initially, it goes all over the place, but then after a while, it settles to this characteristic shape. The characteristic shape is a closed orbit in the frame of the planet. In the rotating frame of the planet, one naturally expects the dissipation would drive things to periodic orbits in their reference frame. And so that's why virtually any dissipation has this effect. And so let's see how this works, how this leads to resonant repulsion. So here I'm showing, this is a test particle. The x-axis is the semi-major axis of the test particle, and the y-axis is eccentricity. So initially the test particle is here, the planet is off to the left, I'm really stealing things to the planet. This is the location of the 2 to 1 resonance, and I'm starting off the test particle here at this eccentricity. As I had it evolve with some damping, what happens is eccentricity falls. Right? If I damp a system, its eccentricity will damp to 0. It damps towards 0. Then it gets stuck at this curve. This is the curve where it closes in the reference frame of the planet. This is called the forced eccentricity. And it's basically stuck here. It's stuck at this curve. You're continually to damp. You're continuing to remove energy from the system, because any damping tries to remove eccentricity, but it's stuck to this curve. So what does it do? So if you've learned about accretion disks, you're familiar with what happens if you have energy dissipation in a disk system, and what happens is it spreads, right? Accretion disk spreads because you reduce energy. And that's exactly what happens here. Remember, there's a planet off to the left here, and we're adding damping. This guy is stuck to the curve. We continue to remove energy, so it climbs up to this forced eccentricity, and jumps across, and it goes to the left loop, and it goes to the right of the curve. So basically, having damping in the presence of a resonance naturally shifts planets from the inside of the resonance to the outside of the resonance. And this effect is driven by the resonance. So it's only near the resonance where you expect this palop to happen. So this shows a simulation of the effect. Where I start off with 2 planets inside the 2 to 1 resonance. This is their period ratio. Actually, they're inside the resonance. Yeah, damping, and they're pushed outside resonance. This shows the observed distribution of period ratios, but now I'm plotting it as delta. So instead of period ratio, I normalize it to delta, which is the fractional distance resonance. This shows the observed palop outside of resonance. And this shows what happens if initially I start out with a flat distribution of delta, where the planets are all randomly oriented, and I add some dissipation to the system. And so initially all these guys evolve under resonant repulsion, and you get a deficit to the left and a peak to the right. The time scale here is unknown. It's a function. Remember, I have somewhat arbitrary damping. And I don't know how strong the damping is going to be. All I know is if there's damping, you'll get this effect. And you can quantify this effect by saying, what is the delta after a certain times t? In other words, how far does the delta, how far does this peak move after a certain times t? And it scales like this. So to get the observed pileup, a delta of a few percent, you can say what t over t damp is. In other words, given the observed peak, you can say how many e-folds of damping these planets underwent. And so based on this, we infer that the planets have undergone 100 damping dampers. They've experienced 100 damping dampers. So many, many, many damping dampers. You may be wondering, this introduces one of the projects, potential projects, which there are other higher order effects of resonant repulsion. And we can ask not just for planets near first order resonances, but you can also ask for planets near three body resonances when all three bodies undergo resonance involving all of their angles. And there are a number of Kepler systems which are found with three body resonances. So what I've done in preliminary simulations is if you start with two planets in a right configuration, and you add damping to them, then the outer pair move out and the inner pair move in this funny way. And you see that three-body angle is naturally driven to a three-body resonance. So one of the goals is to quantify this. Another goal is to quantify higher order resonances, like second. If you have, instead of 2 to 1 and 3 to 2, if you do like 3 to 1. Because there are features seen in the Kepler distribution at 5 to 3 especially. And it would be nice to understand what So to get this pileup, all you need to assert is there's some form of damping. I don't know what the cause of the damping is, which I'd love to find out. There's sort of three candidates. One candidate is tides, which is probably too weak, so it probably doesn't account for it. Although Norm's found a way to enhance tides by having multiple planets. But even so, it's still on the edge of being too weak. Another possibility is if these planets were in a gas disk, then the gas disk naturally imparts damping with a very, very fast damping time. Gas disks are very dissipative. The problem with this is you run into the migration problem. Then maybe there's a way around the migration problem. A third possibility is that maybe these planets were embedded in a planetesimal disk, similar to where Uranus and Neptune were thought to migrate from, be affected by a planetesimal disk. And the planetesimal disk could add damping on the planets. So this last 2 minutes leads me to the second project, which I'll talk about. So this is putting in damping into a simulation, an n-body simulation, a formation simulation. So to give some background, let's imagine the planets just formed in situ. In other words, let's say the Kepler planets, initially you start with a number of very small bodies, and they stir each other, and then whenever they hit each other, they stick, and they grow bigger and bigger. Maybe, let's say that maybe this is how the Kepler planets form. So this is we looked at by other people. This shows a sample simulation that done. So what this shows is the x-axis is time, and the y-axis is the initial planets. So this triplet of blue curves shows the planet with this semi-major axis and this periapsis and apoapsis. And they have a bunch of planets which are evolving. They go all crazy, and they emerge from the system. And we'd like this final system to be our Kepler system, to be consistent with our Kepler system. The problem is that it's not consistent, and there are basically two problems. One is the eccentricities, as you can tell between the eccentricities are too big. And the eccentricities are codified by the distance between the apoapse and the periapse. That's one problem. And the second problem is that planets are too far spaced. Here you see there are only 4 planets in a decade of semi-major axis, whereas many of the Kepler systems have 10 planets. So this is too violent to the system. This is one simulation. This shows 25 simulations. Each line shows the peri and periapo planets. It's a consistent result. You get very widely spaced planets. So what I'd like to do, or have what you do, is to add damping to the system to see how this modifies it. So one naturally might expect that damping can prevent this violent excitation. It will prevent such high eccentricities and such wide spacing. So this shows a sample simulation where now I just sort of randomly select some damping time. So I selected a damping time of around 10 to the 5 years. This might be consistent with what one might expect from a planetesimal disk. And it lasts for around 10 million years. Although at this stage it's just sort of arbitrary. And what you see is as you run the planets in the presence of damping, they start to excite each other, and some of them cross orbits, but then eventually they're damped because there's damping, and then they end up with their spacing between like the blue and the yellow and cyan is much closer. And so this ends up with a system of 8 planets per decade. And this happens for many simulations. And so this shows the final period distribution in those sets of simulations. There are actually 100 simulations here. This is the actual observations, and this is the period ratios that emerge from this. And you do see parallax at 2 to 1 and 3 to 2, natural to what would be expected from the resonant repulsion. But also you do see other features. So for example, this bump in the data is the 5 to 3 resonance, which I can't explain yet. And you also do see this bump in the simulations. So this will also tie into the first part to try to understand how this comes about. And also this peculiar bump, which seems significant. I don't know for resonance. Okay, thank you.
Questions? So I have one. So what do we learn from Kepler 2 then? K2?
Well, nothing yet.
Will we learn as much as we did?
No, so
the
well,
dynamic?
not for planetary. The real problem is it doesn't get as many planets in the system. It doesn't allow for systems as the sun. And what I've been taking advantage of in almost everything I talk about is a high multi-system, many planets in the system. So not many fewer. It could surprise us, like Kepler surprised us. So maybe if they look at different locations in the galaxy, they might.
So, as you know, Brad and I had a hard time explaining there's too many singles. Presumably you have even a worse problem if you know if it's less final. You have too many multi-planet systems versus one multi-planet system.
Right. So, and one possible route, which we see in simulations like this, is if maybe this is a total speculation, but maybe after you put in damping and you let the damping go away, there's still some systems which are on the edge of instability, and they could become.
They have a lot of
Yeah, about 50%. Many of them that we see are on the edge of instability, and the Shin is about.
Questions?
It's a quick question. What kind of damping do you improve in this simulation?
So the damping is more or less arbitrary. So the type of damping that I use is one that conserves angular momentum. It damps energy, but removes angular momentum. It damps energy, but conserves angular momentum. But it's almost independent of the details of the damping. Most things.
That's artificially modified energy.
Well, you might in the code. And the simplest way to do it is just add in a dVdt equation. You can add minus v over damping, and that basically does almost everything. You have to be careful they don't spiral. The dynamics, so
Is it the total energy or the energy of multiple area motion?
well, as long as it was definitely the energy of energy number for motion.
And what's the time scale of this particular experiment?
So that was this. So it was damping time is 10 to 5 years, and it lasts for 100 volts to get the right power.
We would just get back to the isolation mass.
Well,
Because that's the whole point about the isolation mass. In the sense that when the system is very quiet, because of damping like underlying gas disk, and so their feeding zone is only within 5 of those frequencies.
So
you clear out everything, you get the isolation.
well, the spacing depends on the damping. So I know that it's not.
Or, yeah, I mean, if you have very little damping, of course, it overrun the isolation mass because the excursion is larger than this minimum feeding zone, which is plus minus 5 kilojoules. Okay. The absolute minimum is square root of 12, but it's probably closer to 5, and those are the feeding zones.
So I guess the minimum spacing is the hill zone, but this is above the minimum. So as you gradually
It's not the hill zone, it's 5 times the hill zone.
Well, so I haven't checked that. I know you can get them more closely spaced than this if you have more damping. I've run different types of simulations, different amounts of damping. You can get them more closely spaced than this.
in one orbit, one synodic orbit, on a circular orbit, you will reach from the opposite side within square root of 12 to get inside the orbit.
That's right. But this is
So-
not, so all I'm saying is that this is more widely spaced in the hill zone.
Yeah, but you can't, what I'm trying to say is you can't get closer to square root of 12, but times the hill spacing. And it's typically 5 times. And if you dam very efficiently, that's the whole concept from Savronov made this argument. And it is based on that people deduce this isolation.
I agree, that's the minimum spacing. Anything, if you gradually reduce damping, you have wider spacings with bigger masses. All I'm saying is this is beyond that isolation mass limit. We also know that the Kepler planets themselves are above the isolation mass, like a factor of 3 or 5.
That may be because you have eccentricities.
Exactly.
The
This
hill
is
zone
crossing.
is strictly.
Exactly, these guys are crossing
Only
each other's
meaningful
orbits.
for circular orbits, and if you have any eccentricity, the energetic constraints break down completely.
Right.
In practice, they don't. I don't know.
But as long as the eccentricity is above the hill velocity, so there's a characteristic threshold where you
I worked this out one time ago, together with this version too, so you have the influence of eccentricity, maybe it will make sense.